Heat engines are designed to take heat as input and convert it into useful mechanical work, and to do this over and over again in a cyclic fashion. Differences in temperature are needed to operate a heat engine. Ideally, the high-temperature reservoir contributes heat as needed from its infinite reserves such that its own temperature doesn't drop. Mechanical work is extracted from the heat engine, and the low-temperature reservoir accepts leftover heat without its own temperature climbing. The first law of thermodynamics is about conservation of energy. The change in internal energy of a system, delta U, is equal to the heat added to the system minus the work extracted from the system. Over the course of an entire cycle, the internal energy of a heat engine must be unchanged so that it can repeat. Therefore, the work done in a cycle is equal to the difference between the heat entering the engine, QH, and the heat exiting, QC. The efficiency of the heat engine is defined as the ratio of the work extracted divided by the heat energy put into the system. By the first law, this becomes 1 minus QC over QH. Since the efficiency can never exceed 1, the first law tells us that a heat engine can never produce more work than the heat energy put into it. Heat energy from a low-temperature source is less effective in a heat engine than heat energy from a high-temperature source. Heat from a high-temperature source is very useful and is characterized by a small amount of entropy. Heat from a low-temperature source is less useful and is characterized by a large amount of entropy, where a change in entropy is defined as the ratio of Q divided by the Kelvin temperature T. The heat, QH, that flows out of the high-temperature reservoir leads to a small reduction in the entropy of the reservoir. Delta S equals minus Q hot over T hot. The work produced by the heat engine has no entropy associated with it. The small amount of heat flowing into the low-temperature heat reservoir increases the entropy of the low-temperature reservoir by a great amount. Thus, the net change in entropy due to one cycle of the engine is a positive increase. The second law of thermodynamics tells us that any heat engine must increase, or possibly maintain, the entropy of the universe. It is the rejection of heat into the low-temperature reservoir that ensures this. One heat engine that does not increase the entropy, for which delta S equals 0, is the Carnot engine. The reduction in entropy due to large amounts of heat flowing out of the high-temperature reservoir is exactly compensated for by the small amount of heat flowing into the low-temperature reservoir. Thus, the ratio of Q hot over T hot equals the ratio Q cold over T cold, and the efficiency may be written as 1 minus T cold over T hot. This makes the Carnot cycle the most efficient possible. Note that the efficiency is still less than 1 unless the low-temperature heat reservoir is 0 Kelvin, whereas the first law states that a heat engine cannot produce more work than the heat it uses up. The second law tells us that a heat engine can't even produce as much work as the heat it uses up. Let's consider the individual processes that a heat engine might utilize as steps in its cycle. Often the cycle of a heat engine is traced on a plot of pressure versus volume. This analysis is helpful as the mechanical work performed by a given process is given by the area under the PV curve. When the gas in the heat engine expands against the environment, it performs positive work. When the environment compresses the gas, the engine is doing negative work. One interesting process is the so-called isothermal process, where the system is approximately held in thermal equilibrium with a heat reservoir and therefore held at constant temperature. This process must occur slowly in order for the temperature to be maintained. From the ideal gas law, we see that the pressure is inversely proportional to the volume. A log-log plot will yield a straight line with the slope of the line equal to the exponent of v. The slope is -1 in this case. The opposite extreme process takes place so quickly that no heat enters or leaves the system. This process is termed adiabatic. Now the pressure is inversely proportional to the volume to the power gamma. A log-log plot of an adiabatic process will yield a straight line with a slope of negative gamma. Gamma is the ratio of specific heat at constant pressure to specific heat at constant volume, and is always greater than 1. It takes more heat to raise the temperature of a gas at constant pressure when it can expand and perform work than to raise the temperature when the volume is kept fixed. Thus, Cp is always greater than Cv by adding 1 unit of R to the specific heat. Statistical mechanics tells us that each degree of freedom of energy storage in the gas molecules will contribute 1/2 R to the specific heat at constant volume. If the thermal energy added to molecules gets partitioned into a large variety of different motions for the molecule, then the temperature will not rise as much. Suppose the gas were monatomic, like helium or other noble gas atoms. Then there are 3 modes of energy storage for the gas molecules. These are the 3 translational directions in space for storing kinetic energy. Thus, Cv is 3/2 R, Cp is 5/2 R, and gamma becomes 5/3. For diatomic molecules, the thermal energy can be used to either translate the molecules in 3 directions or rotate them in 2 directions. Note that a diatomic molecule, like a pencil, takes little energy to rotate about the length axis. Thus, for diatomic molecules, Cv equals 5/2 R, Cp equals 7/2 R, and gamma becomes 7/5, which is 1.4. In comparing PV curves, one finds that the isothermal curve is flatter than a diatomic adiabatic curve, which is less steep than a monatomic adiabatic curve. Similarly, with log-log plots, we find that an adiabatic expansion or compression can reveal information about the number of atoms and the shape of atoms in the gas molecules. The most utilized heat engine on the planet is the internal combustion engine modeled by the Otto Cycle. The power stroke consists of adiabatic expansion at high temperature, which puts out a lot of mechanical work. The next stroke involves the opening of a valve to the atmosphere to release the hot gases and take on fresh air-fuel mixture. No mechanical work is done at this stage since the volume stays fixed. The air-fuel mixture is now compressed adiabatically to a higher temperature, at which time the spark ignites the fuel, causing a rapid rise in temperature and pressure. The cycle is back where it began. The area beneath the upper adiabatic curve represents the work put out by the engine. The work beneath the lower adiabatic curve represents the work done on the system. The net work is given by the difference between the work done by and on the gas and is represented by the shaded area enclosed by the curves of the cycle. The efficiency can be measured experimentally from the PV plots by taking the ratio of the net work to the work done by the upper adiabatic process. In theory, the efficiency of the Otto cycle depends on the compression ratio, the ratio between the maximum and minimum volumes, and gamma. A larger compression ratio leads to a more efficient engine. The device used in these experiments is the adiabatic gas law apparatus, or PVT apparatus. Plug in the device, connect the cables from pressure, volume, and temperature respectively into channels A, B, and C of the Science Workshop interface. Put the stopper pins in the innermost holes to limit the motion of the piston. Clamp the end of the device to the table. We will be performing the Otto cycle in reverse, basically converting work into heat. Yet the analysis of efficiency will be similar as that of the Otto cycle heat engine. With the data collection rate set at 1000 Hz, begin collecting data and then compress the gas adiabatically, that is, as quickly as possible, hitting the stopper at the bottom. Allow it to cool back to room temperature before stopping the data collection. Collect data again and this time expand the gas as quickly as possible, allowing it to warm again to room temperature. This completes the cycle. You may use the XY Smart tool to measure the maximum and minimum volumes V1 and V0 for the compression ratio. The area under the PV curve will experimentally give the work associated with the upper adiabatic process. There are numerical area calculation problems that arise if you include the endpoints in your area calculation. Do not include the endpoints. If in doubt, ask your instructor to check. The area under the lower curve is determined in the similar fashion, again avoiding the endpoints. Subtract the lower area from the upper area to determine the net work, then divide by the upper area to experimentally evaluate the efficiency. Use the measured compression ratio and gamma for diatomic air molecules to compute the theoretical efficiency. Compare the two efficiencies by converting them to percentages and finding the differences in the percent efficiencies. It is useful to compare the efficiency of your Otto cycle to the efficiency of a Carnot cycle operating between the maximum and minimum temperatures of your gas. Plot temperature versus time to determine the two temperature extremes and compute the efficiency the Carnot engine would have operating between these two temperatures. Is your Otto cycle more or less efficient than the Carnot cycle? The second heat engine we will explore is the Carnot cycle, the gold standard of heat engines to which all others must be compared. The Carnot cycle involves isothermal expansion at high temperature. Followed by adiabatic expansion, work is performed by the engine during both of these processes. The system is now placed in thermal contact with a low-temperature heat reservoir and compressed isothermally. The cycle is completed with an adiabatic compression. The net work is given by the sum of the work from the two expansion processes minus the work done on the gas by the two compression processes. Heat is added to the system during the high-temperature isothermal expansion phase. The efficiency is therefore given by net work divided by the work in going from A to B. We begin with the process C goes to D, the isothermal compression at low temperature. Retrieve a clay thermopack from the freezer and apply it to the cylinder. Monitor the system until the temperature reaches approximately 15 degrees Celsius below room temperature. This may take 10 minutes. Now with the data collection rate set at 1 Hz, start collecting data and slowly compress the piston in the cylinder. When you reach the volume representing point D in the cycle marked on the piston rod, stop compressing and stop the data collection. Set the data sampling rate to 1000 Hz. Record data and rapidly compress the handle down to the stopper for adiabatic compression, step D to A. Place your thermopack in the microwave for no more than 2 minutes and place it back around the cylinder. After several minutes, the pressure will rise with the mounting temperature back to the highest point consistent with point A. Now with the data sampling rate back at 1 Hz, isothermally expand the gas until point D is reached again, and then stop the motion and stop recording. Set the data collection rate back to 1000 Hz, hit record, and quickly expand the gas adiabatically until the handle hits the upper stopper pin. Use your cursor to drag and find the areas under each process, remembering to avoid the endpoints. The two compression processes involve negative work. The two expansion processes involve positive work performed by the engine. The measured efficiency of your Carnot cycle is the net work divided by the heat added between points A and B. That is, the work performed between A and B. Examine a graph of temperature versus time for the two isothermal processes and measure their mean temperatures. From these you can determine the theoretical efficiency of your Carnot cycle as 1 minus Tc over Th. Compare theory and experiment. Also add up the change in entropy around the entire cycle to see if it sums to 0. This preservation of entropy makes the Carnot cycle the most efficient heat engine possible, even when the efficiencies, typically below 20% at these temperatures, seem wasteful.